Keep watching to the end of this video for a special Astrum announcement. If I tell you to imagine a telescope, what do you see? Perhaps you picture an old wooden cylinder with lenses at both ends, similar to one that Galileo Galilei first used to gaze up at the heavens and see the moons of Jupiter. Or maybe your mind is constructing a cathedral-sized dome with mirrors as big as tennis courts, like the telescopes high up in the mountains of Chile and Hawaii. Or you could even be drifting onto visions of enormous dishes, like the infamous Arecibo telescope, that once captured radio waves from across the cosmos. What you probably aren't imagining is a cubic kilometer of ancient ice under the surface of our planet's south pole. And yet, deep below the frigid landscape of Antarctica, there lies precisely this. A strange telescope in one of the most inhospitable environments on Earth, designed to observe not light, but instead one of the most unusual and elusive particles in the universe. I'm Alex McColgan, you're watching Astrum, and today we're joining the IceCube Observatory in its hunt for neutrinos, also known as ghost particles. If you stood on this icy surface, you might not be aware that some of the rarest events in the universe are being observed beneath your feet. Located at the most southerly human-occupied base in the world, the Amundsen Scott South Pole Station IceCube makes use of the very ice in which it is built to observe high-energy neutrino particles. But why? Why this extreme environment and weird design? Because neutrinos are weird. Really weird. Neutrinos are fundamental particles, like quarks and electrons. Most of these neutrinos arrive at Earth from the Sun, where they are released from the nuclear fusion reactions raging inside its core. Other neutrinos will have come from more cataclysmic origins such as a supermassive black hole, supernovae, or any other cosmic event with enough energy to rip atoms into their subatomic particles. Similar to electrons, neutrinos belong to the lepton family of particles, meaning that they do not interact with other matter through the strong nuclear force that binds other subatomic particles like protons and neutrons together. Unlike electrons, they are neutral and have almost no mass whatsoever. This lack of charge and tiny mass means that they can only interact with other particles through the weak nuclear force, giving them their ghostly quality and making them one of the most difficult particles for scientists to detect, so much so that even when we do measure their presence, it is only through the impact they have on other particles. If that wasn't spooky enough, neutrinos can also pass through our entire planet without acknowledging the existence of a single atom in the crust, mantle, core, or any other layer of the Earth, flying straight out of the other side completely unnoticed. There are trillions of neutrinos surging through you every single second. And yet, over your entire lifetime, there is only a 1 in 4 chance that even one of those neutrinos will interact with an atom that belongs to your body. Most of these neutrinos are arriving at Earth from the Sun, where they are released from the nuclear fusion reactions raging inside its core. Other neutrinos will have come from more cataclysmic origins like supermassive black holes, or supernovae, or any other cosmic event with enough energy to rip atoms into their subatomic particles. Here we find further demonstration of the neutrino's complete refusal to engage with matter in the universe. Photons, created in those same nuclear reactions, may take 1 million years between bursting out of the Sun's center to leaping off the surface into space. They are constantly absorbed and emitted in random directions over and over again by the atoms in our star, resulting in a long meandering path to escape. Neutrinos, instead, zoom straight out of the Sun in just 2 seconds, traveling at almost the speed of light itself. As far as standard model particles go, neutrinos are certainly the more coy and antisocial of the group, but on occasion they do mingle with other matter and in the process, can create a drama of energetic particle events cascading out in their wake. It is this cascade IceCube is trying to observe. Suspended down between 1.5 and 2.5 kilometers in the darkness of the ice shelf are 5,160 detectors arranged into a lattice cube. Down here, the Sun's rays have been completely swallowed up by the thousands of meters of compressed ice that lie above, and yet, these detectors, called DOMS, are in fact light detectors. I already said that this telescope is not observing light, at least, not direct light reaching us from sources far out in the universe. Neutrinos are so elusive, the DOMS must detect them indirectly, by taking advantage of a cascade of reactions that starts with a neutrino colliding with an atom of frozen water, and ends in a blue flash. When the DOMS detect a blue flash, the scientists know that either a cosmic ray or a neutrino has passed through the ice, and the hunt begins to find its cosmic origins. The key step in this cascade, and therefore the key to identifying a neutrino interaction, is the muon particle that springs out of the initial collision between neutrino and ice. As the newly created muon hurtles through the incredibly clear and dense ice, it can exceed the speed it takes light to move through that same ice. Now let's be clear, nothing can move faster than light.
In a vacuum, but in other materials, such as ice, liquid water and glass, light can be outpaced. This isn't a violation of physics, but rather a consequence of light slowing down more than other particles within the ice. As the muon races beyond its photon counterparts, it generates a shockwave of blue light expanding in a cone-shaped pattern out from its path, an eerie phenomenon known as Cherenkov radiation. Cherenkov radiation is most commonly associated with nuclear reactors, eerily emanating through the water that surrounds their cores. This blue hue in nuclear cores, and strangely also down in the ice of the South Pole, can look peaceful and atmospheric, but is in fact the quantum equivalent of the sonic boom that roars out from a supersonic jet plane flying overhead. In this case, the plane moves through the air, pressure or sound waves are pushed out in all directions. With the jet speed building up towards the speed of sound, the waves in front start to bunch up, forming a shock front of high pressure. When the plane exceeds the speed of sound, it smashes through the shock front, causing a rapid change of air pressure. This is the sonic boom. The shock front then travels out in a cone, trailing behind the aircraft, which observers will hear as a thunderous clap. In the case of the muon, the particle is not pushing air, but instead disturbing the electric fields of atoms in the ice with its electromagnetic charge, polarizing the water molecules. As the molecules depolarize back to their usual state, they release the energy that forced them into polarization as photons of blue light traveling out in all directions. This is happening all along the path the muon takes through the ice. The traveling muon is triggering emission of electromagnetic waves from the water ice molecules, which radiate out into all directions, producing a cone of emission in the direction of the muon's motion. If the muon was traveling slower than light in the ice, there would be no wave front, and all the expanding light spheres would destructively interfere with each other, cancelling out to complete darkness. But since the muon is traveling faster than light, a shock front of constructive waves in the form of blue light is created. The thousands of digital optical modules of IceCube are primed to detect this signature blue light flashing through the ice. The minuscule time differences between when one DOM registers the flash and when the neighboring DOMs detect it allows the scientists to triangulate the neutrino and trace its path back through the ice, and ultimately through the universe to its origin. These orb-like detectors are marvelous, intricate devices designed to detect the faintest luminal hints in the icy mass. Each DOM is encased in a 13-inch spherical glass pressure case, which protects the electronics inside from the extreme cold and high pressure of the Antarctic ice. Botner et al., 2005. Inside, there is a photomultiplier tube sensitive enough to detect even a single photon, along with various components that amplify the signal and convert it into digital data, which is then transmitted up the cables to the surface. And with so many detectors making up this three-dimensional array, there is a lot of data. A whole terabyte of measurements are captured every day, with 100 gigabytes of that being beamed by satellite to scientists across the planet for them to comb through in search of their ghostly quantum target. Within this trove of data lie the imprints of many particles arriving from beyond our atmosphere. The vast majority are cosmic rays. IceCube detects around 275 million of them daily. Cosmic rays are interesting in their own right, but serve as an obscuring curtain of noise to those seeking neutrino interactions, which occur a million times less frequently, with only around 275 detected daily. But even with the 100,000 neutrino detections that IceCube makes each year, almost all of them are generated in our own atmosphere as debris from collisions of cosmic rays with atoms in the gas that surrounds our planet, and not from cosmic origins themselves, the key word here being almost. On the 22nd of September, 2017, an exceptionally bright burst of Cherenkov radiation was registered by IceCube's array of detectors. Working together, the DOMs used the tiny time differences between when they each detected the flash to triangulate where in the sky the flash must have originated. What they found was surprising. a single neutrino had passed through the ice after likely arriving at Earth 3.7 billion years after it was emitted from a blazar, a supermassive black hole with a beam of charged particles coming out of it. The direction this neutrino was traveling in when it collided with our planet traced it back to an active galactic nucleus in the middle of the Orion constellation. It was the first time in human history that a neutrino detected at IceCube could be directly traced to a cataclysmic event outside of our solar system. That small, fleeting burst of blue light frozen into the ice marked an enormous leap in understanding our universe. This is the potential power of IceCube. Not just detecting neutrinos, but revealing their history, tracing their path, and in so doing helping us find their origins in the chaos of the universe. Because when we detect a high-energy neutrino, what we're really seeing is a trail of clues leading to some of the most dramatic and powerful events to occur since the dawn of the universe itself. Today, IceCube is just over halfway through its latest upgrade, with completion expected in 2026. We are still at the beginning of our journey into the weirdness of neutrinos, and IceCube will play an enormous role in the revelations to come. And if you enjoyed this episode, then click the link on the screen now to see more about the ghost particles themselves. Don't forget to like and subscribe. Thanks for watching.